move the arm up. How can you give the
Wait,
input
wait,
to the
wait,
plant from this
wait.
actuator?
I will take the example of a simple motor, okay?
Okay,
In a motor, what is the input? The voltage, right?
right.
And the output is the RPM, okay? The angular velocity of the shaft, right?
Yes,
So let's take RPM as the output and voltage as the input. That is clear?
yes, clear.
Now, in an open loop system, what you do is you kind of just, you just give the voltage, in an expectation that you get some RPM. Okay. But in closed loop, what you do is you actually measure the RPM using a sensor and then compare it to the desired RPM. And then based on that, you decide what voltage should you give. Okay.
Yeah, that's what I'm saying. That here in the picture that you are showing, the
Hmm.
actuator's output is directly given to plant, but actuator's output must be given to a sensor which will predict the RPM, which will estimate the RPM of that motor, and then
Wait,
that
wait, wait.
sensor's output. Yeah,
The sensor measures the RPM and then compare it to the desired RPM, and then based on that, a control signal is given to the actuator, and then the actuator converts that control signal to the actual input. Okay. Because voltage you cannot control, all you can control is actually maybe the entry that you give on if it's electronically controlled system, all you can do is you can control the entry that you type on the, and then based on that the actuator will actually produce that voltage. If you have a so the control signal can directly be going to the plant also. If the plant, is not so huge and it doesn't require much energy, then directly the control signal can go to the plant as well.
yes, sir. That is what I'm
Actuator is
saying.
basically the force generating device. The force can be electromotive force, or it can be a mechanical force, or it can be a hydraulic force. It's a kind of like a, it's the more, it's like that. Do you get it?
Yes, sir, completely agree. But sir, like what I was thinking was this actuator must be put in that actual output part. Like the plant's output must be given to actuator, and it is also given to the sensor, and then sensor's output
Why do you
again.
need plant output to be given to the actuator? How can output is RPM, right? How can you give RPM to the actuator?
So, like you are saying, in this actuator block, the mechanical part is also present, and one sensor is also present, which will calculate the RPM. Is that what you are
No,
saying?
the actuator is basically a voltage. That's it. That's the actuation signal is basically voltage to the motor.
Actuator's input is the voltage,
No, the
right?
actuator's input is what you set on the your keyboard. Whatever you are doing to give the voltage. Okay, if you are using a rheostat to adjust the voltage, then the actuator input will be the rheostat position. So the control signal of the actuator will be something that you can actually play with. Okay, if you're riding a quadrotor using a joystick, okay, the actual actuator for the quadrotor is actually the voltage in the BLDC motors. But the control signal will be the joystick position. Got it?
Yes, got it.
Now for us, if you want to drive a quadrotor, without human, then what you should do is you have to measure all the states of the quadrotor, and based on that automatically compare it to the reference state of the quadrotor, and then determine the joystick position, automatically, by having it automatically moved, or directly deciding the voltage itself based on the measurement on the reference. Okay. Another thing is what you give from the actuator is the input, but apart from that, there may be other disturbances as well. You have to take that into account. And then what sensors technically measure the output, but in addition, they also pick up some noise. So that is where the noise comes in. So disturbances are unwanted stuff at the plant side, and noise is the unwanted stuff in the sensor side that you cannot control. I'll give you a very standard example. Let's say, you want to you know heat water to uh, let's say you want to heat water to, let's say, 90 degrees Celsius. Okay, and then
Okay.
you have already done it many times. You know the quantity of water, you know the specific heat capacity of water, you know the room temperature, so you know how much time you have to, how much how much heat you have to give. So you just do it. That is called open loop. But when you take a thermometer and then you measure the temperature, and then based on that and the reference temperature that you want, based on that you vary the stove position. That will be a closed loop control with human as the controller. If human is, so in closed loop systems, controller can be either a human, or in automatic control, that controller is basically a machine. Okay.
Sir, like in this particular diagram that you are showing, can you give some example, like what can be in the place of controller, what can be in the place of actuator, what can be in the place of plant, and similarly what can be in the place of sensor?
Okay, so let's take this problem. Are you comfortable with this?
Yes, sir.
So here, what do you the here, what do you think is the output?
Sir, the output will be the h of t, the level of h
Yeah.
of t.
So the water level. So the sensor will be the water level indicator. The output will be the h of t. Okay. And what goes in? What is the input?
So the input is a qi, like the water flowing inside the
Yeah, the water flow rate, the inflow rate and the outflow rate. Okay. So you can that those are the inputs. What is the control signal?
control signal.
How will you
Um,
control the input rate? How will you control the input flow and output flow practically in a normal household scenario?
Flow rates.
Huh?
Flow rate.
Yeah,
Water
flow
flow
rate. How
rate.
will you control the flow rate? How will you, using a
so the
tap, right?
Yeah, yeah.
Tap
floor,
position.
yeah,
Tap position. Tap position is a control signal. Got it?
yes, sir.
So in a case of a human controlled closed loop control system, the human will see the water level, actual water level, compare it to the water level he wants, and based on that, adjust the tap position accordingly. That is human controlled closed loop system. Whereas in an automatic control system, what you do is you have a sensor that measures the water level, and then based on the reference level that you want, it will itself, the controller will be something that moves the tap position based on the measurement it's got. Okay. So let's say you have some electronic device on the tap to move it, and then the electronic device receives the sensor measurement of the water level, and then compares it with the actual, compared to the reference water level that you have pre-programmed in it, and then based on that it moves the tap. So that will be a automatic controlled machine controlled closed loop system. Okay, for water level. Got it?
Yes, sir.
Yes, sir.
Like sir, in this particular example, uh, first of all, like when professor explained this, he take qi of t. So here I'm assuming that qi of t is the input, and q of t is cannot be controlled. Q of t cannot be controlled.
Q of
But
t, what is simply Q of t? There is nothing called Q of t. There's either Qi or Qo.
yeah, so I'm talking about qo of t. So q of t is independent,
See,
while
you put a
qi.
tap on, if you put a tap on the right hand side, you can control Qo of t also.
Yeah, if I put, but currently qi of t can only be controlled.
Okay, if you
So
put the tap only on the left hand side, then what it means is that you can control only you can only have inflow. You cannot control the outflow. You cannot make UI negative. If you want to make UI negative, you have to control QO. You cannot. Okay, that will be a constraint in the input. Got it?
yes, sir.
But we are not bothered about too technical stuff like that. Okay.
But sir, like
That is called constraints in the inputs. If QI can only be positive, it cannot be negative, because when it is negative, which means If the inflow rate is negative means it's actually flowing out, but you cannot actually control the outflow rate without putting a tap on QO. So that is called a constrained system. Okay, we are not getting into too much technicality. We are just at this moment we want to just identify stuff.
Like sir, I was trying to understand how professor built that mathematical model for this particular single tank system. So
You mean this model?
yeah, so this dh by dt is equals to qi minus q naught, and
Hmm.
y of t is h2 plus nt, which is error.
So what do you,
So
what do you don't understand here?
yeah, so the main problem with this equation that I got is, so qi of t basically is a controlled variable. So when h star minus yt is greater than 0, this means that qi of t must be increased. So hence
QI
professor
of
wrote that
t QI of t should depend on h of t and h
h star
reference. Okay,
minus, yeah, h
for a
star
closed
minus
loop
y of
system.
t.
Yeah,
So the equation that professor wrote, qi of t is equals to k times h star minus y of t. This equation is
yeah.
perfectly correct. Uh, I don't have any problem with this, but the explanation that how professor include qo of t in that particular equation,
The
that is my
explanation.
question.
Okay, slide number. Tell me the slide. Should I go?
I think the single tank system slide is
Huh?
the single tank system slide in which the complete figure is given. Yeah.
Uh-huh.
So yeah, in this slide, can you scroll down? Yeah. So this equation qi of t is equals to k within bracket s star minus yt plus 1 by k q naught t. What is the significance? Why he added 1 by k times q naught of t there?
Okay, okay. Wait. So if you 1 by k q naught of t, if you multiply it by k, you will get just q naught of t, right? So qi of t will be just qi of t will be k times h star minus y plus q naught of t. Okay, that's another way of writing it. Okay, so this is basically what is called the feed forward control.
Okay.
So then, don't bother about this to right now. Okay, see, this is a 12-week course, right? If you ask all the questions in this first week, just don't bother about it too much now. Basically, what happens is, if the reference level is keeping on changing, it changes with time. Okay, let's say I don't know, H star is not constant; it varies with time. Okay, then you require other signals that kind of you know you have to give apart from the feedback so that the system is able to track your reference signal accurately. Got it?
Yes,
Don't
sir.
bother about the equations too much for now, but this is the gist if you want it. Okay. The feed forward controller will basically happens when the reference itself is dependent on time. It's a reference, not a constant set point anymore. It depends on time. It itself is a signal. Got it? So you don't want to track a constant set point. You want to kind of like track a signal varying with time. So for that measurement of h and h star and comparing it to y of t is also okay. But you also have to give other time dependent signals that depend on how the signal will expect to change in the future. Correct? For
Yes,
example,
sir.
let's say your h of t is less than h star of t now. Okay. If you are blindly feedback controller, you want to raise the water level, right?
Yes, sir.
But let's say h star, you know what h star of t is, right? Because references, you know what h star will
Yes, sir.
is.
It is a reference level.
Yes, but if you know that h star will decrease in future, then you should not want to go up, right?
Yes, correct.
So let's say H star is going to go down at the after some time. Let's say the derivative dH star by dt is negative. Then based on that you will kind of want to cancel the increase that you plan now, right? So that is what is coming as Q naught of t. Okay. I
Got it.
think
Yes, sir.
the name Q naught of t is not the outflow rate here, but it's additional feed forward signal. Okay, I think it should be some change Q naught of t here as some u of t. Then that will be less confusing.
Yes,
Got
sir.
it?
Got it.
So
So
change this
basically,
Q naught of t to some u of t, okay, or uf or some f of t, where f is the feed forward signal. Now it is clear?
yes, sir, clear. Because I was confused with this Qi of t and Q of t. I'm trying to assume that both Qi of t and Q of t are controllable. But the equation that
No,
professor
no,
wrote,
Q naught of t, in the equation is not the outflow rate. It is a feed forward signal, okay, that takes action based on the future input. Since
yeah,
see,
got it.
output cannot be known in advance. You cannot know what will happen to the system after 5 seconds. But you know what reference input you want to give at 5 seconds, right? You know what the system wants to be after 5 seconds, right? So the input regarding the input signal, you have the knowledge of the future input values also. So you can utilize that and then to give an extra corrective measure. So that is called the feed forward control. Okay.
Yes, sir.
So again, I'm telling if the reference signal itself is changing with time, and you know the signal in advance. Okay, based on that, you have to take an extra corrective force because what might be so because every control has a delay. If h of t is less than h star of t, and then if you blindly just increase it, it will take some time to increase. But you know that by that time the reference itself would have decreased. It will be a foolish measure to have the increase now. So that is why you need feed forward. Okay, change this q naught of t to f of t. Then I think you'll be fine. This is just an
Yes, sir.
introduction part, so don't. It's good that you notice these things in detail, but yeah. Sometimes notations do mess up. Got it? Any other
Yes, sir.
question?
Yes, sir.
By
So,
the way,
like,
yeah. You're Aditya, right? You're the one who was asking me so far, right?
yes, sir.
Okay, just want to know. Yeah. Any other question, Aditya?
Yes, sir. So the next step, what professor gave us assignment that something to think. So the first question was what causes the level of liquid to increase or decrease in the single tank system.
Okay.
So according to me, the answer should be uh, Qi of t minus Q of t. Is that correct?
Exactly. Yeah. Yeah.
And then he said that think in terms of other conservation laws you would have studied in physics, like conservation of energy, momentum, charge, etc.
Mm.
So is it there like is there any conservation law which is applying here? Like in this question, what causes the level of
So
liquid
in
to
this
increase or
question, technically, there is no conservation law that you need to be worried about. Okay.
okay.
Conservation law comes about when you have multiple storage elements. Okay. Of course, you can
Multiple
always,
storage elements.
you can always, talk about conservation of the energy of each molecule of water that is coming. That is irrelevant here. Okay.
Right.
Not all conservation laws in physics are relevant to a control problem. Okay, only some are. Don't bother too much about it.
And the second question was the single integrated model represents conservation of. That was the
Hmm?
second question. The single integrator model represents conservation of this
There is
model.
no convolution here. I don't know. There is no convolution here. Where do you see a convolution here?
Convolution. No, no, I'm not talking about convolution. It is conservation. The second question professor asked.
Conservation.
Yeah,
There
I
is
think
no
it's
conservation
conservation
law that
itself.
is directly relevant here because the moment you have Qi and Qo, water level will not be conserved. If Qi is equal to 0, Qo equal to 0, then the water level is conserved. Got it?
Right. No, like I'm
So
just asking because
you can
professor
say the
has.
water level itself is conserved, but you have to ignore the inputs. Okay, if you ignore the inputs, then if you focus on the unactuated system, then it has a conservation law. The water level is just constant. But that's an uninteresting system because already it is one dimensional because there is only one variable of interest and it is constant, nothing much, right?
Yes, sir.
So when you have only one dimensional system, conservation law, having a conservation law is useless because it will just stay constant. There is only one quantity and that is the conservation you want to be talking about. Then that is uninteresting, right? Because control means you want action, things to be changing.
Right, sir.
Any other question?
So one more thing is there, like professor just asked that how to choose K. So,
Ah, so what do you think?
sir, I think
I
uh,
don't want you
so,
to say, give an exact mathematical analysis. Tell me intuitively what will happen if k is too low, what will happen if k is too large, and
so my understanding, which is based on my previous course, analog electronic systems, where we have an amplifier, and if the gain is very large, the error, like the system will respond faster. So the
mm,
error will be low if the
mm.
amplitude is quite high. That's what my intuition is.
Yeah. So if
So
the thing is, yeah, if k is very low, then you feed not much feedback. You are correcting only little bit based on feedback. So its system will take slow to respond. Correct? That is obvious, right?
yes, sir.
If K is very high, what do you think will happen? There are two problems. One problem is the actuator will kind of, even for a little error, K is very high. The actuator signal has to be very high. That will spoil the actuator.
Yes, sir.
The other thing is, okay, if the feedback gain is very high, your system will kind of start performing will become unstable instead of stable. Like in feedback amplifiers also it happens, so the oscillations grow when you have studied that, right?
Yes, sir.
Okay, so imagine this, uh, let's say, okay, every system has some time constant. It takes some time to respond. Okay, so for example, RC circuit has its own time constant, that is a product of R and C, 1 by RC, right? So that tells you in what time scale the system operates. Okay, mechanical systems operate in seconds. Electronic systems can operate in millisecond time scale if they are of very sufficiently high frequency, right? And thermal systems operate on minutes. You can't change temperature of a room within a second, right? Correct.
Yes, sir. Correct.
So imagine this happens. Let's say you are having a if you let's say you're sitting in an AC room. This kind of happens a lot if you kind of think about it. And let's say you want uh, you know temperature to, let's say the current temperature is the room temperature is 30, and you want to bring it down to 25. So there is an error. Correct.
Yes, sir. Correct.
So let's say you're having a very high feedback gain. So you switch on the compressor, very strongly.
Yes, sir.
What happens? The system also responds. But when it comes down quickly, and when the system has come to 25, you cannot stop it, right? Even if you stop it instantly, it will go further cooling down. The system will take some time to respond.
Yes, sir. Correct.
And then now you will kind of decrease the compressor suddenly, at a very high gain, and then so system will also go, but it kind of becomes uncontrollable after that,
Some
because AC.
oscillations will happen.
Yeah, so and if you are very greedy, the oscillations will grow instead of decaying. Even water heater also it happens. Some people, they want water very quickly, so they, give a lot of power to the water heater. Okay, but the water heater might have reached your set point, but if you switch off, it will continue heating because of the inertia, correct? So, and then it will take some time to again settle down wherever you want.
So,
Yeah.
so what is your main object? Like your we should focus on, like we should control how much time what we are trying to figure out. Like timing is our main constraint, or what is the
Okay,
main
what I'm
constraint?
saying is if your control gain is too high, the system will respond fast. But if the actuator, is kind of fluctuating quickly, and the system doesn't have the time constant of the system is not in that range, then it will become unstable rather than stable. That's what I'm saying. It will kind of perform, it will like kind of oscillate very
Okay,
much.
sir. Okay.
So then, like, how will decide the value of K? because it cannot be larger and it also cannot be smaller.
Yeah, that the exact analysis, that's what the entire course is about, okay? The entire course is about choosing case. Okay.
Okay.
Don't bother about that, okay? That's why you're here. So
So,
yeah, so I'll give the intuition is basically okay, even when you're eating, okay, for some if you feel a sense of hunger and fullness, right? But
Yes, sir.
that is not actually instantaneous. There is a delay actually. If you take food, it will take some time for you to feel full. Correct?
Correct.
So some people, if the feedback gain is very high, what it's like, even when you are feeling a little hungry compared to your usual feeling, you will stuff it with a lot of food because you're not getting that full sensation. But if since you have taken a lot of food, what will happen is, after some time, you'll feel actually more than full. You'll feel like vomiting. So that is what happens when the feedback gain is too high. Okay, the feedback gain should be chosen based on the system's time constants and all the exact details is what the entire course is about. You will learn in subsequent weeks. For now, you just start to identify all these components in a given system. Okay.
Okay, sir.
Any other questions?
Sir, can you share this module 11 lecture on PDF?
I thought the slides are already shared with you.
Like in where it is mentioned, in important lines it will be there, yes.
Huh?
supplementary control on the dashboard.
Supplementary?
On the dashboard, there is a part
On the dashboard,
supplementary
there is?
content. Supplementary
Where?
content
Where?
on the dashboard.
What do you exactly mean the dashboard? I see only 5 files here. The other one is actually a repeat of. Yeah, there's only 5 files here. I don't
There
get
is
what
a
you mean by.
on our lecture dashboard, IDM dashboard, there is a supplementary content part, and
Okay,
there
I
is a
haven't
drive
seen
link.
it, so I will ask and let you know. Okay, I don't know what you're exactly talking about. You want the supplementary content, huh?
No, no, no. I'm saying like it's available on the dashboard, on the IITM dashboard, where we saw our lectures and submit uh,
Okay, I'm new to all this, so I don't exactly know. Maybe I'll think about it next time. Any other questions you have?
No, sir.
Yes, sir. In the first lecture itself, professor gave some questions. Which of the following are open loop, closed loop feedback, and feed forward systems?
Hmm.
So we have traffic light control system, cruise control in automobile. So if we
Hmm.
can discuss which kind of systems are there.
So cruise control is also feedback, right? So correct? Because the sensors measure the actual speed based on the reference speed, you controller decides. What should be, what is the autopilot is basically an example of again another example of feedback control.
And sir, why cannot it be feed forward?
Feed forward means your reference should change with time. For example, in autopilot, it is feedback as long as you just want a level flight. But when you're landing or taking off, it's feed forward because the desired altitude is changing with time when you land and when you take off, right?
Okay, got it.
So at that time, you should also have feed forward signals.
Sir, but reference point is also changing in the feedback also because you are measuring the output and giving it back to the controller, right?
See, measuring the output always changes with time. I'm talking about reference signal, reference output. What you want, see, what actually happens always changes with time. But what you want, whether it is constant or varying with time, that's what you should ask. Of course, the speed will change with time. That's what in a mechanical system. But what speed you want? Does that is it a single number or
Uh,
is it a
Correct.
okay?
Got it. Yes.
Input and output will always be changing with time. Can't see the slide. I don't understand what you mean supplementary column.
Actually, sir, they want the access of the slides. So one of the persons say that the slides are available in the dashboard.
In our portal, it is. In portal board, there one supplementary is mentioned actually.
Okay, right now I don't. I have only these 5 slides with me. Okay,
Yeah,
these
yeah.
are the. So you are saying that there is some supplementary material also that I'm not showing you. That's what you're saying.
No, sir, no, sir. He's saying like in the supplementary portal, this PDF is not uploaded. He's saying like that.
Okay, so you don't have access to the slides. That's what you're saying.
We have the access.
Then what do you want?
I don't want anything. I'm telling to Amit, like, where you
Yeah,
find
then
the
what do you
slides.
want? Whoever asked it, what do you want? Wait, I'll open the chat
Sir, I
box.
just checked it is there.
Should I proceed or not?
Yes, sir. Like cruise control is feed forward, right? What about traffic light control system? I think
Wait,
it
cruise
is
control is feed forward. Do you want the ship's reference speed to change?
ship's reference free. Cruise control should be feedback, right?
Yeah, feedback is all should be there always. I'm talking about whether in addition it is feed forward as well.
So I think it depends on the application present in cruise control. If what you
Exactly.
said that
That's what I
reference
was.
point
Yeah.
is okay,
Because
and
yeah.
yeah.
Next, next.
Next was your traffic light control system.
Okay. What do you exactly mean traffic light control? Depending on, see, the traffic light control, normally in an open loop situation, what will happen is the traffic lights will, fluctuate in a predetermined period. Okay, that's what open loop traffic controller means.
Yes, sir.
Whereas a closed loop traffic light controller, what it will do is it will see how many people are there, how many people want to go from one lane to another at a given time, and based on that, it will see how much time
Based on
this
inputs, it will react. You're saying.
no, based on the output, based on the people, based on the traffic, it will react. Based on the traffic, it will decide the signals timing. Whereas an open loop traffic light controller will just do its own thing. It's on. It will just flash on red and flash off the red in a predetermined period. Got it?
Yes, sir. Got it.
So here the input is the traffic light. The output is traffic. So when the signal itself depends on the output, the traffic that is flowing, traffic that is there in the jam, then it is closed loop. Okay.
Sir, like the closed loop system and feedback system, I think both are
Yeah,
the
the
same.
same.
Okay.
See, when you denote dependencies through a diagram, you draw the arrow from the input to output. In a feedback system, we also have an arrow from the output to the input. So they kind of close a loop. If you see left to right, from input to output, and then right to left from output to input, they close a loop. That's why feedback systems are also called closed loop systems. Okay. Whereas when you just have one arrow connecting input to output, there is nothing to close there. It's just unidirectional. Got it?
Got it.
You
So the
must have
second
studied
point
it in
was
your signal flow graph and all, right? I don't know. Have you studied that in your signals and systems class, signal flow graph?
yes, sir. In
So there
signal
you have
processing tool.
closed loop. You kind of talk about closed loop, right? You close some.
Yes, sir.
Yeah.
We
So
did that.
that's the idea here. Okay. So here, if you see in the diagram, you go from the reference signal, control signal, and then output, and then you can kind of come back to the reference signal to the sensor. You kind of have a closed loop. Whereas if you don't have the sensor controller part, you just can travel from left to right. You cannot travel back from right to left. Okay.
Yes, sir. And the second example was chasing a target of 213 in 20 overs in the cricket.
Once again, I'll just charge my laptop. Chasing a, yeah, can you repeat again? Chasing?
Chasing a target of 213 in 20 overs in cricket.
Is that your assignment problem?
Uh, the question was given in the lecture one.
Okay, so yeah, obviously it's a feedback control, right? Because depending on how many runs you want, and how many runs you have, you kind of play accordingly, right? I don't know much about cricket, so play.
And sir, what about human walking? I think it should be feed forward.
Human
Walking, human walking.
human walking, yeah, it is feedback if you just want to walk or walk at a steady pace, but it's feed forward when you want to have a speed variable desired speed.
Okay, sir. And what about GPS navigation?
GPS navigation also it's feedback because it measures where you are and then accordingly tells you the route, right?
Yes, sir. So it should be feedback.
Yeah.
And the last was appearing for an interview.
Mm.
It should be open loop, I guess.
Yeah, I don't know what exactly is the input and output in an interview, so I can't say much.
Okay.
Anyway, don't bother about this too much. Week one is just introductory. It's just for warming up. Yeah. Anything else you want to discuss? I think this is the
Uh,
part where all these the other things, static, dynamic, time varying, time invariant, all you might have learned that already in signals and systems.
yes, sir. But just the definition part, not the use case,
Not the.
not the application part. They just told,
So you
professor
want
just
me to give
mentioned the
one
definition.
example of each?
Yes, sir. Like it will be very good if you.
Okay, wait. So linear, nonlinear, at least you know. So linear means it obeys superposition and homogeneity. That you know.
Yes, sir.
So all linear circuits in electrical and electronics are actually linear systems as well in a system theoretic framework. And all linear mechanical systems like a linear spring, a system made up of linear spring where the restoring force is proportional to the displacement from equilibrium. And you have linear dampers where the damping force is proportional to the velocity. All those all those mechanical systems made of interconnected linear devices, they are also linear in a system theoretic framework as well. Okay.
Yes,
Whereas
sir.
nonlinear means you can have, any system is actually nonlinear. Linearity is just an ideal approximation that you make. No spring is perfectly linear, no resistor also is perfectly linear, right? If you plot the VI graph of a resistor or the charge voltage graph of a capacitor or a voltage and rate of change of current graph for an inductor, they all won't be straight line, right? You
Yes,
just
sir.
take a small area and then say approximately say this is a straight line and you just get it over with. So linearity is actually something like an ideal, simplifying ideal that you kind of approximate rather than actually find it. And then you have okay, this is okay. Lecture 2. Static system means the output at a given time depends on the input at a given time. That's it. For example, take a resistor and let the voltage be the input and the current be the output. So the current at a given time t is linearly related to the voltage at a given time t through resistance. I of t is equal to 1 by R times V of t. Okay, that is a static system. Whereas in a dynamical system, the output at a time t will not just depend on the input at the time t, but will also depend on the output at a previous time. Got it? So, for example, uh, wait, nothing. Okay. Take an RC circuit, okay? So you have V is equal to, and let's say the charge on the capacitor is the output. Got it?
Yes, sir.
So take a simple RC circuit where the voltage is the input and the charge on the capacitor is the output. So you'll have V is equal to IR, but I is dq by dt, right? So V is equal to dq by dt times R plus what? Uh, Q equal to CV, right? So V equal to 1 by C times Q of t, right?
Yes,
So
sir.
Q of t not only depends on V, it also depends on dq by dt, correct? And
Yes, sir. Correct.
dq by dt is basically sophisticated version of finite difference. Q of t minus q of t minus delta t divided by delta t, where limit delta t going to 0. That's only dq by dt means, right?
Yes, sir.
So the moment you have a derivative in the system, what it means is what happens at a slightly previous moment is also influencing the system.
Yes, sir. Because differentiation and integration are memory
Exactly. So if
conference.
you have dq by dt, it means it's not just q of t, it is q of t minus delta t as well. So it means your output depends on not only input at a given moment now, but the output at the previous moment as well. So you have dynamical system. And the amount of the differentiation that you have you can determine the order of the dynamical system. If you have only q of t and dq by dt, then it is a first order system. If you have q of t, if you have an RLC circuit, then you have di by dt, which is d square q by dt square, then that's a second order dynamical system. Okay. So a static system is a zeroth order system because there is no derivative. If you have one derivative, it is first order, which means you have one integrator storing element. If you have two derivatives, which means you have two integrators in the block diagram, then it is second order system. Okay. Do you get this?
Yes, sir. Completely.
The next is time invariant and time varying system. Okay. So here you have input and output, that is okay, but what about the parameters appearing in the system? Do they change with time or do they not? For example, take an RC circuit. So you have V is equal to 1 by C times Q plus R times dQ by dt, right? So here the voltage is the input, Q is the output, Q and then dQ by dt is the derivative of the output, okay? But the remaining constants, they are the parameters, right? C and R. Do the resistance and capacitances themselves, are they changing with time or are they not?
No, sir. No.
So they are not normally, but at sometimes they can. Okay, for example, due to at a shorter time scales, they are actually time invariant. But if you leave a resistor for 1,000 years, do you think it will be the same?
No, sir. Resistance will
Yeah.
decrease.
So the time variance also depending on the scale of interest. So systems are maybe time invariant for a shorter period. Whereas if you want to analyze on a longer time scale, it may be time varying. Got it? Or if your resistor is kind of a special material which heats up very easily and it changes depending on the heat received, then that is a time varying system. Got it?
Yes, sir. Got it.
Yes, sir.
So okay, everything again depends on not only depends on what you want, it also depends on your interest. If you want to analyze the if you want to analyze the motion of a ball that is thrown, then the acceleration due to gravity is constant, right? 9.8. But if you want to analyze the motion of a satellite, the gravitational acceleration is not a constant parameter anymore. Okay, So depending on the scale of interest, you kind of you can also mean whether system is time varying or time invariant changes. Let's say you're having a room temperature as your parameter in your system. So it is time invariant for a shorter time scales, but over a longer time scales, like over the course of a year, the room temperature might change, right, depending on the season. So in that sense, so for longer time scales, the room temperature is actually time varying. And if your system parameter, one of the system parameters is room temperature, then it's a time varying system. Okay. So time invariance mathematically means if you give the input with a delay of, if you give the input after 100 years, you get the same output as you give now with the same input, except that it will also be after 100 years. Got it?
Yes, sir.
So if a delayed input signal, so if u of t gives y of t, then if you give u of t minus 100, then the output will be y of t minus 100, the same y but shifted by 100. So if that happens for all delays, whether it is 100 or 200 or 1000, then it is a time invariant system. Again, some things may be time invariant for small delays, but time varying for larger time scales. So that is what again matters. So that is time invariance and time variance. The next is causal and non-causal system. So in a causal system, Q of, the output depends on the outputs at the previous time scales, correct? In a normal, system. But if the output Q of t depends on the charge, depends on the output at the future also, then it is non-causal.
Yes, sir.
Systems technically they are not. Most systems are actually causal. Most systems in the real world are actually causal. The state at now depends on the state at a previous time, but they don't depend on the state at the future. That is nonsense for most systems. But it's a mathematical ideal that will be kind of useful when you to go for controller design. Any other questions?
No, sir.
Others? Okay,
So,
I'll
sir,
just
if
follow
we
the.
take a single equation like f of t is equals to t. Okay,
Huh?
so
What?
is it f of t is equals to t? Okay,
Okay.
as the time changes, then it will also change linearly.
F of t. What do
So
you mean by
the
f of t?
a function.
Do you want me to go to a certain slide which you are referring to?
No, no.
Okay, then please speak slowly and a little bit loudly if possible.
Okay, so I'm asking like if we take a function f of t is equals to
Hmm.
t. Okay,
Hmm.
so like if we delay it, then it will be causal or non-causal.
Causality is for a system, not a signal. Causality in control systems is defined for a system, not a signal. Got it?
But system will work on the signal.
A system is called non-causal if if its output signal at the present moment depends on the output signal at the future moment, apart from the past. For example, the amount of nutrition that you have now depends not only on the food that you have eaten now, it also depends on your fitness at the previous moment, right?
Yes.
So the same amount of food, but starting with different initial conditions may it leads to different outputs. So that is a causal system. But saying that your fitness right now depends on your fitness in the past, that is okay. But saying that your fitness right now depends on the fitness in the future, that is nonsense because nobody knows what is going to happen in the future.
Okay.
This is just an just for the sake of exhaustion. We will not be dealing with non-causal systems in our course. Okay,
Okay.
non-causal systems do happen only when a signal is not a physically meaningful signal. Okay, so it's something that you for systems that are not physical, but you kind of hook up in your computer. Okay, and I can always write a computer algorithm, right, where q of t is some function of q of t plus 1, correct?
Yes.
So I can always run the system from future to the past rather than from the past to the future. So, non-causality comes when you run the system when the system runs backward in time. But no system practically runs backward in time. But sometimes you can make up systems in your computer computationally that run backward in time. In such instances, when you're not dealing with physical systems, but when you're dealing with computational constructs, so then you non-causal systems are kind of useful. But otherwise, in this course, will be bothered about control of causal controllers for causal systems. Okay.
Okay. Okay. Thank you.
Next. Okay, I'll call you each of you out one by one. What is this 24F110? What's your name? Please speak up. See, if the point of connecting a live session is to you to speak up. Otherwise, you can just watch videos at home, right? If you just want to listen, you can might as well listen to the lecture videos. So please speak up. Otherwise, I'll mark you absent if you are not speaking even once, or even in the attendance, even in this call. I'll mark you as absent. Okay. 24F11011000132. Are you there? Or are you
Yes, sir.
just
Yes, sir.
yeah? Any questions you have?
No.
Thank you. Aditya, any more questions?
No, sir.
No, sir.
Amit?
No, sir.
Subhashish? Are you there, Subhashish? Alkesh?
Yes, sir. Earlier I had a doubt, but it's been cleared.
Okay, thank you. Vinayak?
Yes, sir. No doubts for now. It is
Dhruv?
cleared, sir.
Dhruv?
No, no doubts.
Okay, Amit? Amit?
No, sir.
Okay then, we'll close it then. Thank you.
Thank you, sir.
Yeah, see you on
Thank you,
Friday.
sir.
Vasumati will be handling the session on Friday. See you.
Thank you, sir.